All right, today we're going to talk about one of the most powerful and maybe one of the most misunderstood ideas in all of technology, the matrix. Seriously, this is the hidden language that builds and powers so much of our modern digital world. So, let's dive right in. Have you ever stopped to think about how a video game renders these incredible, immersive 3D worlds? Or how an AI can look at a photo and instantly pick out a face? Or, how economists try to model the entire chaotic global economy? I mean, these things seem worlds apart, right? Well, it turns out, from the amazing animation in movies to the engineering that makes sure our buildings don't fall down, all the way to the seriously weird world of quantum mechanics, they all share a secret: common language. That's right, the Matrix. And no, I'm not talking about the movie, although honestly, the concepts aren't totally unrelated. Over the next few minutes, we're going to build a basic toolkit so you can understand what a matrix is and why it's just so incredibly important. Okay, first things first, let's just strip away all the complicated jargon and get right to the heart of what a matrix actually is. That's it, that's really all it is. Don't let the fancy name fool you. When you get right down to it, a matrix is just a box, a simple grid made for holding numbers in a really organized way. Honestly, just think of it like a spreadsheet. So, if we put on our formal hats for a second, the definition is a rectangular array of numbers arranged in rows and columns. The rows are the ones that go across, and the columns go up and down. We even describe its size that way by saying rows by columns. So a matrix with 3 rows and 2 columns, we just call that a 3 by 2 matrix. Simple. And here's how we keep track of every number inside. We give each one an address. We use this little subscript, Aij, where the I tells you the row number and the J tells you the column number. So if I say A23, you just go to the second row, third column. Boom, there's your number. It's like a coordinate system for a grid. Okay, so now we know what a matrix is. What can we do with it? Let's start with the most basic moves in our toolkit. Simple stuff like addition and scaling. Adding 2 matrices together is probably exactly what you'd think it is. It's super intuitive. First, you just have to make sure they're the same exact size. Can't add a square to a long rectangle, right? Once you've confirmed that, you just add the numbers that are in the same spot. Top left gets added to top left, bottom right to bottom right, and you just go through the whole grid like that. Next up is something called scalar multiplication. Now, scalar is just a fancy math word for a single number. And all this means is you take that one number and you multiply every single element inside the matrix by it. So if we multiply this whole matrix by 2, every number inside just gets doubled. It's like using a magnifying glass to scale the entire grid up. All right, let's get to the real powerhouse of our toolkit, matrix multiplication. Now, this one's a little trickier, but trust me, this is where a matrix stops being a simple spreadsheet and starts becoming a powerful engine for transformation. This is where the magic happens. Okay, but before we even get into how it works, there is one critical golden rule you absolutely have to remember. With normal numbers, we know 3 times 5 is the same as 5 times 3. With matrices, not a chance. Multiplying A by B is almost never the same as multiplying B by A. The order you do it in matters a lot. So how do we do it? Well, we follow something called the row times column rule. To get just one number in our new matrix, we take a row from the first matrix and a column from the second. Then you multiply their matching elements, first with first, second with second, and so on. And then you add all those little products up. And that sum is your new element. You just repeat that dance for every single spot to build the final matrix. So let's add a couple of advanced tools to our kit. Think of these as the master keys that let us use matrices to crack some really tough problems. I'm talking about the determinant and the inverse. First, the determinant. This is a very special single number that you can calculate, but only from a square matrix, one that has the same number of rows as columns. You could almost think of it as a unique fingerprint or a quality score for that matrix. Okay, fine. It's a special number. But so what? What does this one number actually tell us that's so important? Why do we care about it? Well, its main job is to tell us if the matrix has an inverse. And you can think of the inverse as a literal undo button. So if a matrix performs an action, like rotating a character in a game, its inverse is the matrix that rotates it right back to where it started. It's the ultimate CTRL plus Z. And here's where it all connects so beautifully. A matrix gets to have one of these powerful undo buttons if and only if its determinant is not 0. If that determinant is 0, we call the matrix singular. It means the action it performs kind of collapses things in a way that you can't perfectly reverse. So that one little number, the determinant, tells us whether a problem can even be solved. Okay, we've built our basic toolkit. We have our grids, we know how to add, scale, and multiply them, and we've got some advanced tools. So now, let's go all the way back to the beginning and see how this stuff actually builds the world around us. So where do you see this? Well, every time a 3D character moves on screen, that's matrix multiplication transforming its coordinates in space. When an AI learns, it's literally adjusting millions of numbers inside enormous matrices that act like a brain. From economics to engineering, matrices are the silent, invisible engine making it all happen. And this slide, right here, this is why they are so unbelievably useful. On the left, you've got a system of equations. It can get messy, fast, but on the right, the exact same problem, written as a single clean matrix equation, AX equals B. This is what allows computers to solve thousands or even millions of these equations all at once. It's the power of elegant organization. So if you take one thing away from this, let it be this. Matrices are not some dusty, abstract math concept. They are a real, practical, and incredibly logical toolkit for taking on some of the most complex problems we face and solving them with elegance and efficiency. So now you have the foundational tools. You get the grid, you know the basic moves, you've even seen the power-ups. So the only question left is, if you could take this toolkit and apply it to any problem